The equations of quantum field theory allow us to calculate the behavior of subatomic particles by expressing them as vibrations in quantum fields. But even the most elegant and complete formulations of quantum field theory, like the Dirac equation or Feynman's path integral, become impossibly complicated when we try to use them on anything but the most simple systems. But physicists tend to interpret "that's impossible" as "I dare you to try." And try they did. First they expressed these impossible equations in approximate but solvable forms. Then they tackled the pesky infinities that kept appearing in these new approximate equations. Finally, the entire mess was ordered into a system that mere humans could deal with, using the famous Feynman diagrams. To give you an idea of how messy quantum field theory can be, let's look at what should be a simple phenomenon: electron scattering, when two electrons repel each other. In old-fashioned classical electrodynamics, we think of each electron as producing an electromagnetic field. That field then exerts a repulsive force on the other electron. At least in the simplest cases, the Coulomb equation governing this subatomic billiard shot is really easy to solve. But in quantum field theory, specifically quantum electrodynamics, or QED, the story is very different. We think of the electromagnetic field as existing everywhere in space, whether or not there's an electron present. Vibrations in the EM field are called photons, what we experience as light. The electron itself is just an excitation, a vibration in a different field, the electron field. And the electron and EM fields are connected. Vibrations in one can cause vibrations in the other. This is how QED describes electron scattering. One electron excites a photon, and that photon delivers a bit of the first electron's momentum to the second electron. It's arguable exactly how real that exchanged photon is. In fact, we call it a virtual photon, and it only exists long enough to communicate this force. There are other types of virtual particle whose existence is similarly ambiguous. We'll get back to those in another episode. This is a good time to introduce our first Feynman diagram. The brilliant Richard Feynman developed these pictorial tools to organize the painful mathematics of quantum field theory, but they also serve to give a general idea of what these interactions look like. In a Feynman diagram, one direction is for time, in this case up. The other axis represents space, although the actual distances aren't relevant. Here we see two electrons entering in the beginning and moving towards each other. They exchange a virtual photon, this squiggly line here, and the two electrons move apart at the end. But Feynman diagrams aren't really just drawings of the interaction. They're actually equations in disguise. Each part of the Feynman diagram represents a chunk of the math. Incoming lines are associated with the initial electron states, and outgoing lines represent the final electron states. The squiggle represents the quantized field excitation of the photon, and the connecting points, the vertices, represent the absorption and emission of the photon. The equation you string together from this one diagram represents all of the ways that two electrons can deflect involving only a single virtual photon. And from that equation, it's possible to perfectly calculate the effect of that simple exchange. Unfortunately, real electron scattering at a quantum level is a good deal more complicated than this. For that reason, this simple calculation gives the wrong repulsive effect between two electrons. If we observe two electrons bouncing off each other, all we really see is two electrons going in and two electrons going out. The quantum event around the scattering is a mystery. There are literally infinite ways that scattering could have occurred. In fact, according to some interpretations, all infinite intermediate events that lead to the same final result actually do happen. Sort of. We talked about this weirdness when we discussed the Feynman path integral recently. Just as with the path integral, to perfectly calculate the scattering of two electrons, we need to add up all of the ways the electrons can be scattered. And this is where Feynman diagrams start to come in handy, because they keep track of the different families of possibilities. For example, the electrons might exchange just a single virtual photon, but they might also exchange 2 or 3 or more. The electrons might also emit and reabsorb a virtual photon. Or any of those photons might do something crazy, like momentarily split into a virtual antiparticle-particle pair. Those last 2 events are actually hugely complicating, as we'll see. With infinite possible interactions behind this one simple process, a perfectly complete quantum field theoretic solution is impossible. But if you can't do something perfectly, maybe near enough is good enough. This is the philosophy behind perturbation theory, an absolutely essential tool to solving quantum field theory problems. The idea is that if the correct equation is unsolvable, just find a similar equation that you can solve, then make small modifications to it, perturb it, so it's a bit closer to the equation that you want. It'll never be exact, but it might get you pretty close. In the case of electron scattering, the most likely interaction is the exchange of a single photon. Every other way to scatter the electrons contributes less to the probability of the event. In fact, the more complicated the interaction, the less it contributes. Here, Feynman diagrams are indispensable. It turns out that the probability amplitude of a particular interaction depends on the number of connections, or vertices, in the diagram. Every additional vertex in an interaction reduces its contribution to the probability by a factor of around 100. So the most probable interaction for electron scattering is the simple case of one photon exchange with its 2 vertices. A 3-vertex interaction would contribute about 1% of the probability of the main 2-vertex interaction. However, it turns out that for electron scattering there are no 3-vertex interactions. However, there are several interactions that include 4 vertices, and each contributes about 1% of 1% of the 2-vertex interaction. And this is true even though those complex interactions are very different to each other. They include exchanging 2 virtual photons, or one electron emitting and reabsorbing a virtual photon, or the exchanged photon momentarily exciting a virtual electron-positron pair. And more complicated interactions add even less to the probability. So with Feynman diagrams, you very quickly get an idea of which are the important additions to your equation and which you can ignore. Perturbation theory, with the help of Feynman diagrams, make the calculation possible. But that doesn't mean we're done. Including all of these weird intermediate states really opens up a can of worms. This is especially true for so-called loop interactions. Like when a photon momentarily becomes a virtual particle-antiparticle pair and then reverts to a photon again, or when a single electron emits and reabsorbs the same photon. This latter case can be thought of as the electron causing a constant disturbance in the EM field. Electrons are constantly interacting with virtual photons. This impedes the electron's motion and actually increases its effective mass. The effect is called self-energy. But if you try to calculate the self-energy correction to an electron's mass using quantum electrodynamics, you get that the electron has infinite extra mass. This sounds like a problem. To calculate the mass correction due to one of these self-energy loops, you need to add up all possible photon energies. But those energies can be arbitrarily large, sending the self-energy and hence the mass to infinity. In reality, something must limit the maximum energy of these photons, but we don't know what that limit is. The answer probably lies within a theory of quantum gravity, which we don't yet have. But just as with perturbation theory, physicists found a cunning trick to get around this mathematical inconvenience. It's called renormalization. Obviously, electrons do not have infinite mass, and we know that because we've measured that mass. Although any measurement we make actually includes some of this self-energy, so our measurements are never of the fundamental or bare mass of the electron. And that is where the trick lies. Instead of trying to start with the unmeasurable fundamental mass of the electron and solve the equations from there, you fold in a term for the self-energy corrected mass based on your measurement. In a sense, you capture the theoretical infinite terms within an experimental finite number. This renormalization trick can be used to eliminate many of the infinities that arise in quantum field theory. For example, the infinite shielding of electric charge due to virtual particle-antiparticle pairs popping into and out of existence. However, you pay a price for renormalization. For every infinity you want to get rid of, you have to measure some property in the lab. That means the theory can't predict that particular property from scratch. It can only make predictions of other properties relative to your lab measurements. Nonetheless, renormalization saved quantum field theory from this plague of infinities. The quantum vacuum is a seething ocean of activity. Virtual particles appear and vanish from nowhere in seeming violation of our intuitions about the conservation of mass and energy. We saw in our recent episode that we can thank the Heisenberg uncertainty principle for this bizarre behavior. It tells us that there's a quantum fuzziness in the amount of energy contained at every point in space, a non-zero, zero-point energy in the quantum fields that can briefly manifest as particles. This suggests that space itself contains energy. But how much energy? Quantum field theory predicts that the energy of the vacuum should be up to 120 orders of magnitude greater than the measured value. It's one of the greatest unsolved problems in physics. Let's talk about vacuum energy from a theoretical standpoint. From the perspective of quantum field theory, every point in space is represented by a quantum oscillator, one for each elementary particle type. Higher energy oscillations represent the presence of real particles. However, even the lowest possible energy oscillation, the one corresponding to the absence of particles, the so-called vacuum state, has some energy. To satisfy the Heisenberg uncertainty principle, the vacuum state of any field oscillation must be half of the tiny Planck constant times the frequency of that oscillation. Now, that's a minuscule amount of energy. Except to properly describe a perfect vacuum, every single possible frequency mode at every point in space must have that amount of energy. To calculate the density of energy of the vacuum, we should add this tiny energy over an infinite range of frequency modes for all fields. Now, multiply a finite energy density, no matter how small, by infinity, and you get infinite energy density. We'll get back to whether the idea of infinite vacuum energy is actually possible. It certainly sounds a bit excessive, so maybe we can avoid it. Let's think in terms of the electromagnetic field. What if there's a maximum possible frequency for virtual photons? Then our sum of frequency modes would be finite. Now, it sounds like a hack, and it sort of is, but we're getting desperate. And anyway, there's an almost sensible cutoff for photon frequency. It's where photon energy is equal to the Planck energy, or 10 to the power of 19 giga-electron volts. This is where our understanding of physics breaks down. Until we develop a theory of quantum gravity, we can't say whether photons above this energy are possible. So, if we add up the vacuum energy, including virtual photons, all the way up to the Planck energy, we get a finite number. A very, very large finite number. The energy density would be 10 to the power of 112 ergs per centimeter cubed. This back-of-the-envelope estimate was first made by John Wheeler and Richard Feynman, who noted that one teacup of space with this energy density would contain enough energy to boil all of the oceans on the planet. Yet, even if vacuum energy did have a value this high, in fact, even if it were infinite, we may not notice, at least according to quantum theory. In fact, in both quantum mechanics and classical mechanics, a particle's equations of motion depend only on changes in energy. The 0 point of the energy scale is irrelevant. As long as the vacuum energy is the same everywhere, then it's inaccessible to us as an energy source. We're going to come back to that point in an upcoming episode, so you'll be able to knowledgeably scoff at 0 point energy perpetual motion machines. Long story short, a crazily high, even infinite vacuum energy doesn't affect the predictions of quantum field theory. Just redefine the 0 point to whatever you want and you're good to go. However, you can't be so cavalier with general relativity. Einstein's theory tells us that any form of energy produces gravity, and what matters is the absolute amount of energy, not relative deviations. Vacuum energy should produce a gravitational effect, and a huge vacuum energy should produce a huge gravitational effect. That effect would be seen in two ways. An energy of space itself should cause exponential expansion, at least in the case of an already expanding universe. It should also massively increase the spatial curvature of the universe. Now, this is all extremely unintuitive, and we spent 5 episodes trying to give you a sense of why this is true. Now, feel free to jump down that rabbit hole if you haven't already, but the upshot is that if vacuum energy really did have the enormous value predicted by theory, then our gently expanding, geometrically flat universe would not exist. The realization of this fact in the early days of quantum field theory was the beginning of what would become the vacuum catastrophe. But it wasn't a full-blown catastrophe yet. There was still a way out. If some fields can have extremely large positive 0 point energies, then perhaps others have extremely large negative 0 point energies that cancel them out. An extension to the standard model of particle physics called supersymmetry may partially allow this. It gives all particles a supersymmetric counterpart that may precisely cancel out their vacuum energy. Now, basic supersymmetry only allows us to cancel out photons down to the so-called electroweak energy, which brings the predicted vacuum energy down to a mere 10 to the 47 ergs per centimeter cubed. But perhaps a yet deeper theory allows perfect cancelling down to 0. For a while, theorists assumed that something like this must be happening, meaning the vacuum energy was really 0. It was a glimmer of hope that catastrophe could be averted. That is, until we discovered dark energy. In the late 90s, astronomers discovered that the expansion of the universe is, in fact, accelerating in exactly the way we would expect from a non-zero vacuum energy. Now, unlike the Lamb shift or the Casimir effect, the observation of accelerating expansion allows us to measure the absolute density of vacuum energy. Assuming vacuum energy is to blame, dark energy weighs in at 10 to the power of -8 ergs per centimeter cubed. Compare that to the number predicted by quantum field theory. There's a discrepancy of 120 orders of magnitude between the two, or 55 orders of magnitude if we use the electroweak energy cutoff instead of the Planck energy cutoff. Now that is what scientists call a catastrophe. QFT can give us an extremely high vacuum energy, or a vacuum energy of exactly 0 if we assume symmetry of positive and negative 0 points between different fields. But a very small, non-zero vacuum energy? That requires what we call fine-tuning. Gigantic positive and gigantic negative 0 point energies would need to cancel each other out down to a very tiny non-zero value. That sounds like a ridiculously unlikely bit of luck if we can't invoke symmetries.
Standard model of particle physics is a pretty humble name for one of the pinnacle achievements of 20th century physics. It takes the mathematical formalism of quantum field theory and uses it to describe every known particle in the universe. But when first developed, the standard model had a pretty major issue. In its early form, none of the particles, not even the matter particles, had any mass. A particle without mass is obliged to travel exactly at the speed of light all the time and never slower. The Standard Model predicted a universe in which all particles acted like radiation, which would imply no atoms or what we think of as matter. Maybe such a universe exists out there, but it's not this one, apparently. The particles of matter, the electrons, quarks, etc., do have mass, so the builders of the Standard Model needed a mechanism to give it to them. And the best candidate for the job was a mechanism developed simultaneously by several people in the early 60s. That mechanism is driven by what we now call the Higgs field, after one of those several. With that field also came the inevitability of a new particle, the Higgs boson. Now, if we could just detect this particle, we would verify this mass-granting mechanism and wrap up the Standard Model. So, the Large Hadron Collider was built, fired up, and in 2012 the Higgs boson obediently appeared with the right mass to make sense of the masses of the other known particles. Nice work, Standard Model achieved. Of course, mysteries still remain. Dark matter, dark energy, the matter-antimatter asymmetry, neutrino masses, how gravity fits into the picture. Quite a few issues actually. But the discovery of the Higgs really did close out the Standard Model as a fully self-consistent theory. But there was one particular detail to sort out with regards to the Higgs, an I to dot, so to speak. If the Higgs gives mass to the particles of the Standard Model, what gives mass to the Higgs? And more importantly, why does the Higgs have the specific mass that it does? It turns out that just as we needed the Higgs to explain the masses of the Standard Model particles, we needed a whole family of new particles to explain why the Higgs has its mass, in particular why it has such a low mass in the range of the other Standard Model particles. So the LHC kept powering up. Physicists expected these new particles to pop out, but there was nothing. It's now been over a decade since the discovery of the Higgs boson, and it's the only new elementary particle that the LHC has found. This seems like a relatively minor problem, nothing that a little more theorizing can't fix, but it's considered such a serious issue by many that it's been called the crisis in physics. Today, I want to convey why some think of this as such a big deal. It all comes down to one question. Why is the mass of the Higgs boson so small? In particular, why is it so much smaller than the current version of the Standard Model predicts it to be? This episode is a follow-on from our two recent ones on the quantum structure surrounding the electron and how that defines the electron's mass. If I stop making sense at any point today, maybe go and check those out and come back, or just absorb all the science words and hope for the best. Let's go step by step. First, the origin of mass. We covered how the Higgs field grants mass to the particles of matter a long time ago. For now, it's enough to know that due to the unusual nature of the Higgs field, it exists in a state of non-zero energy everywhere in the universe. Particles that interact with this field absorb some of that energy, and this becomes their mass, or at least part of it. Once a particle has mass from the Higgs field, it will also gain even more mass from the cloud of quantum fluctuations that surround the particle. We covered that in a lot of detail in the last episode in this series. The mass of the electron comes from both its so-called bare mass, as well as the mass of the swarm of matter-antimatter pairs flickering around it. That leads to quantum corrections to the bare mass, resulting in what we call the dressed mass. Those quantum corrections come from literally every quantum field the particle can interact with, and every energy scale that these interactions can happen at. If we just keep adding up those quantum corrections with no upper limit to the energy scale, we get that the particle has infinite mass. Particles don't have infinite mass, so what's up? Well, it's possible to cancel out some of these quantum corrections because some of them add positive energy, some add negative energy. If the quantum corrections are basically random, then the cancellation in general won't be perfect except by extreme luck. So imagine we discover a particle that has a tiny mass, and we can only explain that tininess as being due to many enormous quantum corrections cancelling out almost perfectly by pure chance. That would seem unnatural. The mass should really be around the scale of the largest of those corrections. We also call such unnatural cancellations finely tuned, because it seems like someone went in and twiddled the knobs of these otherwise unrelated quantum corrections to make the cancellation work. If we see that a particle's mass looks unnaturally small or finely tuned, we typically assume that we've missed something. And we're typically right. There are a few cases where we found some sort of new physics that enables the cancellation of those quantum corrections. This new physics typically works above a certain energy scale, suppressing quantum corrections above that scale. For a given particle, its mass will still receive contributions from random quantum corrections up to that scale. In general, this means the measured mass of any particle will be at around the energy scale where the new physics gets started with its cancellation. In the case of the electron, we figured out that most of the mass cancellation comes from a particular virtual interaction involving the electron's antimatter counterpart. This works all the way down to the low measured mass of the electron. See the previous episode for the deets. An important point is that this works for the electron because it's a spin-half particle, a fermion, which means that it has an antimatter counterpart to assist in this cancellation. More formally, the electron has an extra symmetry, chiral symmetry, that wants to pull the mass down to zero, just as the quantum fluctuations want to increase it. So, new physics that appears that a particular energy can give us a way to avoid piling on virtual mass up to infinity. This phenomenon is seen for other particles too. There are a couple of cases involving mesons, which are combinations of a quark and antiquark pair. For example, the kaon, which is a strange quark combined with either an up or a down quark. The masses of the kaon subtypes are very close to each other. However, when the kaon was first discovered, we tried to calculate that mass difference and found that it should be much larger than expected, and that large predicted mass difference was due to large quantum corrections. This felt unnatural, and so physicists guessed that there must be some unknown physics at a very particular lowish energy to keep the kaon masses in check. They figured that the energy had to be a few giga-electron volts. Shortly afterwards, the charm quark was discovered at 1.5 GeV, and adding the charm to the quantum correction calculations gave us the correct mass difference for the kaon. So, new physics appeared at right around the necessary energy to protect the kaon from being unnatural. Something similar is true for the pion, another meson whose mass difference is protected by the rho meson, which has exactly the right energy to keep the pion in check. Okay, great. So, if the particle mass is small, then we expect to find new physics at an energy scale not too much greater than the particle's mass in order to suppress large quantum corrections. Now back to the Higgs. The Higgs boson is particularly vulnerable to having its mass blown up because of its unusual status as the only spin-zero particle in the standard model. It doesn't have the natural protection that the electron and the quarks have by virtue of their additional symmetries. The Higgs is its own antiparticle, so it doesn't have the same self-cancelling virtual interactions as the electron, for example. Based on the standard model as we currently know it, there is no mechanism to protect the Higgs's low mass at any known energy. Now, we know that the standard model is for sure incomplete. It fails at a certain very high energy. That's the energy of the Planck scale, 10 to the power of 17 times more energetic than the Higgs boson. This is also the scale at which we think gravity and spacetime themselves become quantum. We don't know what happens above this scale, but at the very least we expect fluctuations so energetic that they curve the fabric of spacetime. For sure, there could be mechanisms above that scale to prevent the Higgs mass from becoming literally infinite, but before we even get close to those, we expect there to be fluctuations that should drive the Higgs mass close to the Planck scale. So maybe these extreme quantum corrections get eliminated by chance cancellations. But the chance to randomly tune that cancellation to 1 part in 100 million billion is low, to say the least. It would be the biggest fine-tuning problem in physics. Because of that, physicists expect that other non-random mechanisms are at work at lower energy scales to do the necessary cancellations. In the 1970s, physicists came up with an elegant system to do just that, called supersymmetry, or SUSY. SUSY postulates that every particle, both the fermions that constitute matter and the bosons that transmit forces, have a supersymmetric counterpart. For every fermion there's a supersymmetric boson, and for every boson a counterpart fermion. If these SUSY particles have the right energies, they cleanly cancel out the diverging quantum corrections of the Higgs. And to do the job that they're needed for, the lightest of these SUSY particles would have to have masses not too much greater than the Higgs itself, in which case the LHC should have found them by now, which it didn't. So what went wrong and what does it mean? First up, let me say that supersymmetry might still be right. The LHC has probed up to a particular energy range, and that includes the range where the most parsimonious version of SUSY was expected to reveal the first particles. But there still could be SUSY particles at higher energies, and those could still serve to protect the Higgs mass. The problem is that even if LHC finds its first SUSY particle in the next year, its mass will be too high to completely avoid some fine-tuning of the Higgs mass.
So Zeno's paradox is a problem that's not just of interest to mathematicians like myself, but it's also of interest to physicists and philosophers, and it has been for thousands of years. So Zeno was a Greek philosopher. He lived 2,500 years ago, and he came up with a list of paradoxes. There's about 9 of these paradoxes. The ones I want to talk about, though, are kind of similar. The first one, though, I love, because there's a nice little story with it. So the first one is called Achilles and the tortoise. You've got Achilles and the tortoise in a race. Now the tortoise is slower, of course, so he's given a head start. He's got a 100-metre head start, and then they start the race. Now Achilles sprints 100 metres and he catches up to where the tortoise was. But in that time, the tortoise has moved on. Right? He's moved on 10 metres. So Achilles now has to sprint to catch up with the tortoise again. So he sprints another 10 metres and he catches up to where the tortoise was. Now, since that time, the tortoise has moved on another metre. So Achilles has to sprint to catch up to where the tortoise was. And this keeps happening over and over again. So the paradox is, does Achilles ever catch up with the tortoise? And that's insane. And obviously he must do. We all live in the real world. He must catch up with the tortoise. Another of these paradoxes is basically the same, but it's a bit simpler. I'm holding my hands apart like that. Now I'm going to keep my left hand still. I'm going to move my right hand towards my left hand so that they clap. Now when I do that, you can think of it like I'm halving the distance, and then half the distance again, and then half the distance again, and again, and again, and again. And I half the distance an infinite number of times, infinitely many times. So does that mean that my hands never clap? Is there some sort of force field here stopping my hands meeting? Well, obviously they do. This is the paradox. So what's going on here? How can an infinite process end? What's going on? And this is part of Zeno's paradoxes. I want to give you the mathematician's point of view for this because, well, some say that the mathematicians have sorted this out. Let's say I start with my hands 2 metres apart and then I'm going to join them together. So they start 2 metres apart and then I halve the distance. So I've travelled 1 metre and then half the distance again. So it now travels another half a metre. Then you do that again, you halve the distance again. So now your hands have travelled 1/4 of a metre. And then it's an eighth, and a 16th, and 1/32. And then you keep doing this forever, halving the distance forever. Let's say this does have a value. Let's give it a value. Let's call it S. S for sum. Here's a trick that you can do. First of all, I'm going to multiply by 1/2. I'm going to multiply the whole thing by 1/2. So if I multiply the left-hand side by 1/2, you get 1/2 of S. On the right-hand side, I'm going to multiply term by term by 1/2. So 1 multiplied by 1/2 is 1/2. Actually, I'm just going to write that there. I'm going to leave a little gap. Now I'm going to multiply the 1/2 by 1/2, which gives me 1/4. And I'm doing it term by term, so 1/4 times 1/2 is an eighth. And an eighth by 1/2 is 1/16. Now, I'm going to subtract those two things. If I subtract, on the left I get S minus 1/2 S, which gives you a 1/2 S. On the right-hand side, I'm going to subtract these two lines. So I've got 1, and I've got plus 1/2 minus 1/2, plus 1/4 minus 1/4, plus an eighth minus an eighth. And all the terms cancel out. So all you're left with is 1. Which means, if everything's cancelled out then, you can work out what S is. S is equal to 2. So this would be 2 metres. So your hands would travel 2 metres. Even though it's an infinite process, your hands do travel 2 metres. Now, time is important as well. If each step was taking a second, then that's an infinite number of seconds, or if it was longer than a second. So you would complete your 2 metres, but it kind of takes an infinite amount of time to complete your 2 meters. So time is important as well. So let's say, we'll do it a little bit faster than that. Let's say I move a meter per second. So I'm going to move a meter per second. It's the same working out. If I halve the distance, that would take me 1 second. And then I halve the distance again, would take me half a second, then a quarter of a second. So I could travel 2 meters in 2 seconds, and my hands would clap. So something like this, an infinite sum, behaves well when if you take the sum and then you keep adding one term at a time. So you've got lots of different sums getting closer and closer to your answer. Right? If that's the case, if your partial sums, that's what they're called, they're getting closer and closer to a value, then we say that's a well-behaved sum, and at infinity, it is equal to it exactly. And it's not just getting closer and closer, but not quite reaching. It is actually the whole thing properly. So it sounds like I'm saying that you can complete an infinite process. Now, an infinite process doesn't have a last step. So how can something without a last step be completed? And that's the paradox.
What is and is there a solution?
I have no easy answers for you here. This is a paradox that has baffled philosophers and mathematicians for 2,500 years. I wrestle with it as well. There are greater minds than you and I that have wrestled with this problem in the last 2,500 years. If this melts your brain, don't worry, you are in very good company.
Some of these numbers where the digits apparently go on forever, pi, square root of 2, how do they fit into all this?
Yeah, so if something goes on forever, it's almost like you're asking, like, can I even draw something that with these decimal representations that never finish? And it's the same sort of problem that we've got here. But again, even though that's an infinite process, it can be completed. And I know that's bizarre, but look, if I draw a triangle, okay, that has length 1, that has length 1, it's a right angle, and this has length the square root of 2. So, and there's no reason I can't do that, even though the square root of 2 is irrational, which means the decimals go on forever, even though it's like that, there's nothing stopping me from drawing it. In the same way, there's nothing stopping me from clapping my hands. You can think of this as an infinite process. I'm halving the distance an infinite number of times. But I can still clap my hands. So these 19th century mathematicians had to work out when these infinite sums behaved well and when they behaved badly. And so there's a lot of technical detail behind that. And it does turn out to be rigorous and consistent, which is very important. But some of the tests that you can use to prove that something is a well-behaved sum, well, they're quite easy. I'll show you one. What you can do is if you take one of these terms, I'm actually going to call it A. You take one of them, the nth term, an, you divide that by the one that came before it, and if it's negative, well, you'll make it positive then. If you take those numbers, if those numbers go towards a value, let's call it r, as these n's get bigger. Right, if these numbers tend towards a value, and if that number is less than 1, then it's well behaved. So this was well behaved. Why was this well behaved? Because if you take one of those terms and divide by the one that came before it, you always get a half. Look, a half divided by 1 is a half. A quarter divided by a half is also half. These are all halves, actually. You get a common factor of a half, a common ratio of a half for each one. That passes the test. And that's what this is a test. So it passes the test. This is well behaved. If this was bigger than 1, then it's not well behaved. And that could mean, well, it could mean it goes on to infinity. Or it could mean it's periodic or does something else weird. So it's not well behaved. And the other case is, if this number was equal to 1, we don't know. It could be anything. It could be either. It could be well behaved or not. It depends. So r equals to 1, we're not sure.
What's a series where r is like greater than 1? What can you show me? What's a badly behaved series?
So if it was bigger than 1, then the terms would be getting bigger and bigger and bigger each time. Maybe not in a common ratio way, but well, we were talking about the Fibonacci sequence earlier. So if we had something like that, like 1 and 1 and 2 and 3, and if you divide those, they don't have a common ratio, but actually the ratio is tending to 1.618, the golden ratio. So 1.618 would be bigger than 1, and this would be badly behaved. If you added them together, you would get a number that was going off to infinity in that case, and that would be called divergent. This is well behaved, our example, and it's called convergent. My question to physicists is, if we were literal about this and considered the real world, so that we are actually dividing a distance repeatedly in half over and over again infinitely many times, or dividing the time it takes to complete each step infinitely many times, so it's getting quicker, can you do that? Can you divide space and time infinitely many times? I don't know the answer to that.
If you're in a terrifying event, can you actually see in slow motion like Neo in The Matrix who sees in bullet time? And can you therefore distinguish the flashing numbers at a faster rate than you would be able to normally? In other words, we set the pace of alternating lights just faster than you can normally see, just beyond the flicker fusion frequency. So if your vision speeds up like a slow motion camera, taking in more frames per second, then you should be able to report the number that was being flashed. If on the other hand, you're not actually seeing in slow motion, but instead just laying down more memory, you'd be no faster at reading the display and it wouldn't look like anything to you. So we got 23 volunteer participants to do the fall. And here's how it works. Imagine you're the volunteer. First, we measure your flicker fusion threshold under normal, relaxed circumstances. In other words, how fast I can alternate these numbers before you can't see them anymore. Then we put you on the platform that's winched 15 stories up above the ground. You strap the perceptual chronometer to your wrist, and then you're attached to this belay hook that's dangling way above the net. And we set the speed of alternation of the lights to just slightly faster than you can see any number on there. And you're instructed to keep your eyes on your wrist in front of you. And then, at a moment you're not expecting, the hook releases. During the fall, your only job is to identify the random number flashing on the watch. That's it. If you're having higher temporal resolution during the free fall, the rate of alternation should appear slowed, which would allow you to read the numbers that would otherwise be unreadable. But that was only one part of the experiment. After the fall, we had participants retrospectively reproduce how long their fall took using a stopwatch. So you think back on your fall, and you start the stopwatch when you picture the hook being released, and you stop when you think you hit the net. So you're reproducing it in your mind. And then what you also do is you watch other people take the fall, and you reproduce that memory on your stopwatch as well. So the moment they were released to the moment they hit the net in your memory. And what we found here, consistent with the verbal reports, is that everyone estimates the duration of their own fall to be longer than when they're remembering someone else's fall, the same fall. On average, people felt that their own falls took at least 30% longer. But the surprise came with the results from the perceptual chronometer. No one was able to read the numbers in free fall at a faster rate than they could when they were standing calmly on the ground. And this is not because they closed their eyes or didn't pay attention. We monitored for that carefully. But because they couldn't, after all, see time in slow motion. So despite my subjective experience of falling from the roof, I hadn't, after all, seen my surroundings in bullet time like Neo. Now, this wasn't necessarily the result I was expecting, so we analyzed this data every which way to make sure there wasn't a mistake, and there wasn't. People weren't actually seeing in slow motion. And this was the first step to realizing the link between time and memory. The reason participants reported a longer duration for their own fall, even though they were seeing no faster than normal, comes down to a walnut-sized area of the brain called the amygdala. When there's an emergency situation, the amygdala kicks into high gear and it commandeers the resources of the rest of the brain, and it forces everything to attend to the situation at hand. Now, what's emerged in neuroscience in the last few decades is that when the amygdala gets involved, memories are laid down on a secondary memory system. This is not your normal memory system for everyday stuff, which is taken care of by the hippocampus, but a secondary track, because that's what memories are for. In an emergency situation, when everything is hitting the fan, that's when you want to make sure that you write down all the details for future reference. Now, here's the key. When you play these memories back out, your brain interprets the higher density of data as a longer duration. So, under normal everyday circumstances, most of what happens to you passes right through your system, and very little gets retained. You don't remember much of anything about the details of who you passed on the street today, or all the billboards you saw on your drive, or the color of the car in front of you, or who was in front of you in line at the coffee shop, or much else. When you're judging how long something lasted, the only way you can do it is by looking back and essentially counting up memories. Your brain doesn't get time information for free. It's not like it has a built-in clock. It's made up of billions of cells, and that's all it has to work with. So through experience, it figures out how to make correlations. If I have this much memory I can draw on, then that event must have lasted 10 seconds or 10 months or 10 years. And in this way, duration is always a retrospective estimate, and is totally dependent on how much memory you have, what landmarks you can identify in your memory landscape. And this is why time and memory are linked. But here's what's really important to know about this. Consciousness, your experience of the world right now, it's always a story that's told retrospectively. You're not conscious of anything in the moment, in real time, but consciousness is always about your brain asking itself, what just happened? What just happened? And it pulls the appropriate signals from whatever's available to answer that question. So the reason that police officer remembered his gunshots as being far apart in time is because he was laying down so many details of the footage, so many memories. The car is approaching him, he jumps out of the way, he hits the ground, he's shooting at the side, he shoots at the back window. The closeness of the squealing tires, 100 other details. All that gets stored by this emergency memory storage system. And so when his brain says, what just happened? What just happened? He has such a density of memory that his brain concludes naturally that the event must have been spread out over a long time. And the same goes for that doctor in the motorcycle accident. In a normal 5 seconds of riding along on the road, not much is getting written down in your memory. But when you're on the road, rolling on the asphalt and possibly about to die, your brain is keeping track of everything it can. So when your brain says, what just happened? It has such a density of memories that it assumes the event lasted longer. Now, getting back to the test that I conducted, after I published these results, several people independently said to me, hey, I read your paper, but I think you're wrong because I know that I experienced the car accident in slow motion. So I just asked them, look, the person who was sitting next to you on the passenger seat, did it really sound like they were saying, no? Because if not, then you weren't actually experiencing the world in slow motion. And they have to allow that if time were really stretched out, everything would have to be in slow motion, like a movie. So I want to add, there are some interesting exceptions to the slow motion effect. It only happens in certain circumstances. And the reason is because it depends on whether or not you are expecting or foreseeing the disaster that's heading your way. This is what I call the sliding on ice towards a brick wall phenomenon. If you're in that situation and you see what's coming, then all of your attention is riveted on the details. And so, as we just saw, you're capturing them for later analysis in your memory. So you have the retrospective impression that it all must have taken a long time. But interestingly, when something unexpected happens, when you don't see it coming at all, you don't have time to put your attentional systems on it and write down the memories. And in retrospect, it seems like it happened with no time at all. Once when I was biking, my front tire went into a pothole and I went flying over the handlebars, but I don't remember anything from the event because the whole thing came as a surprise. I didn't see it coming. And this is what happens when people are T-boned in their car by a vehicle that they didn't see. The event doesn't seem to run in slow motion, but instead it's as though time is gone. They were driving along through the intersection, and in the next moment, their car was pinned up against the lamppost without any notion of what the heck just happened. So I noticed when I interviewed people that they described all the predictable things as though they happened in slow motion because they had so many detailed memories about them. But they don't describe the airbags coming out in slow motion because that happens totally unexpectedly. Now let me get back to the big question. What does this link between time and memory have to do with our normal lives? Well, this is why time seems to speed up for all of us as we get older. We all have the impression that a childhood summer seemed to last forever. But when you're older, the summers are here and then they're gone. And years zip by and decades zip by. Well, now you know why. It's because the job of the brain is to build an internal model of the world out there. Your brain is locked in silence and darkness inside your skull, and all it's trying to do is understand the structures of the world so it can operate in it better. And whenever it encounters a surprise, it writes that down and it makes changes to your circuitry. But as you go through life and your brain develops better models of the world, less and less carries much surprise. And this is why you lay down fewer memories as you age. It's because you've seen that situation before and you've met that personality before and you've done that job before. And so the memories that you lay down are much thinner, they're more impoverished. But in contrast, when you're in your childhood, everything is new. And so the richness of that, of your memories, gives you the impression of increased duration. When you are looking back at the end of a childhood summer, it seems to have lasted for such a long time because everything was new. But when you're looking back at the end of an adult summer, it seems to have disappeared rapidly because you haven't written much down in your memory.
How do galaxy spirals rotate? You may think they rotate this way. If this were the case, the spiral arms would become more and more tightly wound, as the stars closer to the center have shorter orbital periods than those further away. This is known as the winding problem. However, observations show that spiral arms persist without significant change over long periods. To address this, scientists proposed the density wave theory, which introduces an alternative mechanism at work. Most astronomers agree that stellar orbits are initially circular, and spiral arms emerge as an evolving pattern. External forces stretch these circular orbits into ellipses and tilt their axes, giving rise to the formation of spirals. In the density wave theory, the arms are not fixed, solid objects, but instead made up of areas of greater density. Individual stars within a galaxy do not physically move along the arms. Instead, they move in and out of the arms as they orbit through the galaxy. This theory provides an explanation for the endurance of spiral arms over time, and there is increasing evidence to support it. Now, let's see a simulation with random particles.
In order to wrench the laws of physics from the reluctant clutches of nature, we need to watch for clues, patterns in its behaviour that can reveal deeper truths. Here's an example. Around 40 AD, Heron of Alexandria noticed that when light moves between 2 points, out of all possible paths between them, it follows the shortest one. He proposed what you might call a principle of least distance to define the path of light. Of course, we now know that light doesn't always travel in a straight line, like when it's refracted by glass or travelling through a gravitational field. It took a millennium and a half following Heron for Pierre de Fermat to propose a solution for the case of refraction. What if light didn't travel the path of least distance, but rather of least time? If light changes speed between media, then the fastest trajectory is no longer a straight line. With this principle of least time, Fermat was able to explain all of the field of optics. It seemed as if we'd stumbled upon a powerful guiding pattern in nature, minimizing principles. What if there was a similar property that could be minimized to determine the trajectories of matter as well as light? There were some efforts, for example, Euler considered properties involving momentum and kinetic energy, but to no avail. In the meantime, Isaac Newton came up with his laws of motion, which gave us the instant and miraculous power to explain the motion of all particles in the universe. To do this, all you needed to do was know the exact vector forces on each body at each time, which lets you calculate that body's exact vector position, velocity, and accelerations at each time. That's doable for, say, a ball flying through the air, but it gets frankly pretty hellish for complicated systems. So maybe we were still in the market for a simple guiding principle after all. It was Joseph Louis Lagrange who found that principle. Consider again the ball flying through the air. We can describe that motion without the painful vectors if we use energy. The ball starts out moving fast, it has a lot of kinetic energy, which it trades for potential energy as it rises, and then back to kinetic as it falls. If you need a refresher on the energy stuff, check out our previous video when you're done here. You can figure out a lot just using energy, like the maximum height the ball will reach, but because energy doesn't include directional information, vectors, it seems that you shouldn't be able to determine the exact path. Except you can. Lagrange realized that a particular combination of kinetic and potential energy had the same minimizing property as does time for the path of light. He found that the ball will always follow the path that minimizes the timed average difference between these energies. In other words, add up the difference between kinetic and potential energy at all time steps during the flight, and you get a number. Then, try the same for any other path that you can imagine. The result will come out higher for every path other than the path that the ball actually travels. Lagrange called this new quantity the action. Formally, it's the integral over time of the kinetic minus potential energies. And that difference in energies itself got the name Lagrangian, which itself turns out to be an enormously important and useful quantity. Lagrange proposed that everything in nature happens in such a way that action is always minimized, and so was discovered the principle of least action. A century later, William Hamilton made the important correction that action is always minimized or maximized. Here's an imaginary graph of how the action can change between paths. You get paths where it's at its lowest and at its highest. Moving objects tend to choose paths where the variation of the action between nearby paths doesn't change much. In other words, where the slope of this curve is 0. And that's true at both the minima and maxima. Most of the time it's the minimum, which is why people still call this the principle of least action, but others call it the stationary action principle. If the principle of least action is true, then it should be possible to figure out the path that any object will take between 2 points, as long as you can find a way to determine which has the minimum action. That sounds hard, but thankfully Lagrange and Euler already did most of the work for us by finding the Euler-Lagrange equations, allowing both physics students and nature to minimize their action. The principle of least action, in combination with the Euler-Lagrange equations, leads to Lagrangian mechanics. When you study Newton's mechanics and then move on to Lagrangian mechanics, it seems almost like a miracle. The hellishly complex equations needed to solve problems using pure Newton seem to just melt away into much simpler forms. This simplicity comes from the fact that with Lagrangian mechanics, we can dispense with forces and vectors in general and only consider the energies. The principle of least action is so powerful that it really seems like it must be telling us something deep about the universe. But what? It's hard to interpret what this action property really signifies. Well, if it really is so fundamental, then it should apply well beyond classical mechanics and into our modern theories, in particular general relativity and quantum mechanics. And perhaps in these we'll find clues as to what the action is really about. Let's start with Einstein's general theory of relativity, which, as we've discussed before, describes the force of gravity in terms of the bending of the fabric of space and time. One of Einstein's motivations in developing general relativity was the fact that Newtonian mechanics failed to correctly predict the orbit of Mercury. If you calculate that orbit using the Einstein equations in their full glory and full gory detail, you get the right answer. But you don't even need to go that far. If the principle of least action really is a fundamental law, then there should be a relativistic version of the action that we can minimize to find Mercury's orbit. After all, planets trade between potential and kinetic energy as they move around in their orbits, just like the ball. It turns out that we only need to make a couple of relativistic corrections to do this. The most important is writing the Lagrangian as a function of something called proper time. In relativity, clocks run at different rates depending on things like relative speed and position in a gravitational field. Proper time is the time that an object will perceive in its own reference frame. If you plug the relativistic Lagrangian into the Euler-Lagrange equation, you get equations of motion correctly describing the orbit of Mercury around the Sun. This shows us that the principle of least action holds up in GR, but it reveals a lot more. First, it means that Lagrangian mechanics based on this principle can be made to be Lorentz invariant. It gives equations of motion that are valid even in the shifting frames of Einstein's relativity. And we also start to learn something about the nature of the action. Once we apply the relativistic corrections, the action simplifies into just an integral over proper time. Let's take a moment to think about that. Before, action was a somewhat vague notion of change in energy. But working with a more precise model of the universe, we see action is much easier to understand. Action is now just how much time is perceived by an observer in their own frame of reference. All objects moving through spacetime move through paths that minimize the time measured on that path. Remember that Fermat figured out that light always travels the path that minimizes its travel time, the principle of least time. Well, it turns out that this is just a special case of a principle of least proper time. The reason for this is that in the classical limit, proper time becomes kinetic minus potential energy for objects with mass. But for objects without mass like light, proper time and time are the same. Okay, it seems like we're getting somewhere. Let's see if quantum mechanics will get us any deeper, or perhaps just make everything more confusing. Let's start with the famous double-slit experiment, as we so often do when talking quantum mechanics. In it, a stream of quantum particles are launched at a barrier with two slits cut in it. When the stream reaches a detector screen on the other side, the individual particles make individual spots, but over time the spots make out this series of bands, an interference pattern. The quantum interpretation of this is that the particle travels between the source and the screen not as a particle with a well-defined trajectory, but as a quantum wave function that represents all possible paths that it could take. The wave function at the screen represents the range of possible final locations for those paths, with some being more probable than others. The particle then appears to randomly select a position from that distribution, but there seems to be a conflict here. The principle of least action says that a particle will always land where the action of the trajectory is at a minimum or maximum. That should correspond only to the central points of those bands. However, we see particles landing at every location in between, albeit with more likelihood the closer you get to these action stationary points. So perhaps action isn't as fundamental as we thought it was. Or perhaps this is telling us something more about what the action really is. Paul Dirac very nearly figured this out. He realized that a quantum analog of the action existed that was related to the integrated time evolution of the wave function. And he realized that this quantity should result in destructive interference in most places, like the dark bands in the double-slit experiment. It would lead to constructive interference only where this quantum action varied slowly, near its stationary points, just like with classical action. But the real action hero of this story is Richard Feynman. Remember that the action tells us about a particle's history along some hypothetical path. Feynman realized that the path of a quantum object could be determined by adding together all possible paths that particles could take, weighted by this quantum action. In this case, the quantum action doesn't come from adding up kinetic minus potential energy, nor the proper time. Instead, it effectively calculates the phase shift that a particle picks up along each path towards its destination. Then it adds the phases of all conceivable paths to that destination. We find that the most likely destinations are those where the phases line up, constructively interfere. This is Feynman's path integral formulation of quantum mechanics, and it exactly reproduces the predictions of previous versions of quantum mechanics, for example, Schrödinger's wave mechanics, that talks about the evolution of a single wave function. This is analogous to how Lagrangian mechanics reproduced Newton's mechanics. And it's no coincidence, because the path integral is the quantum analog of the principle of least action. So what does this tell us about the action? Well, the path integral tells us that a particular final destination is likely if the phases of the many paths that could lead to that destination line up. Away from those special points, very tiny changes in the path lead to rapid changes in the phase, causing those paths to cancel out. As Dirac started to guess, particles tend to end up near the stationary points of the quantum action. In the path integral, this happens for paths that take the shortest path, but not the shortest path through space, the shortest path through something called configuration space. And this configuration space is what ties all of this together. Configuration space is the space of all possible trajectories given our object's constraints. In the case of the ball, configuration space refers to all the places the ball could reach with its current potential and kinetic energies. When we take this to relativity, we see that the configuration space becomes configuration spacetime, where the shortest path minimizes proper time. In quantum mechanics, configuration space could mean phase space, which is the space of all possible positions and momenta, or it could be the more general state space, representing all the quantum states that a system could evolve through. The application of the quantum action principle to the evolution through quantum states underpins modern quantum theory. Back to Paul Dirac, just for a moment. His eponymous equation was derived to describe the quantum evolution of the electron. Well, it turns out that this equation is just the Lagrangian for a spin-half quantum field. And there's a Lagrangian for each quantum field, which describes how that field and its particles tend to evolve. Combining these gives the standard model Lagrangian, which allows us to track the evolution of all quantum fields through configuration space and so predict the behavior of all known particles. And remember, all of this started with Heron of Alexandria studying light 2,000 years ago. He found a very simple and beautiful pattern in nature, and this has been inspiring us ever since, through Fermat and Lagrange and Dirac and Feynman, each seeking a path through the configuration space of ideas, guided by mysterious principles, not least of which is the action, pointing the surest way to the fundamental nature of spacetime.
of the search team. Baker. The team leader. One bullet, straight through the head.
The car veered off an empty road. Why?
Consider like a one-parameter family of states where you start out with that very entangled ground state, and then you just arbitrarily draw a line halfway down the middle, and you start removing entanglement. You change the state so that now, in this case, there's a little bit less entanglement between here and here than there used to be, and here there's even less. And so what happened, I did this, I tried to do this and think about what would happen on the gravity side using whatever tools that were available. And what seemed to happen was that you had this big empty space-time, but then as you remove entanglement, it just starts to deform itself. It starts to pinch itself apart, kind of like you had a big wad of gum and you're just stretching it out. And what happened is that the two edges of the space-time are getting further and further apart. And in some sense, the middle of it is getting narrower and narrower, just like in the picture. Okay, so by removing the entanglement that was there in the field theory state to start with, then it seems that the space, this completely empty space, it actually starts deforming and ripping apart into two pieces. And then you could consider dividing your field theory into more parts and removing more entanglement between more of the parts. And eventually what seemed to happen was that your entire space-time just rips apart into tiny pieces, and you have nothing.
Murli, memory to me is one of those fascinating probes because very smart people, neuroscientists, envision it occurring. We call it the engram. Where is that memory stored? At vastly orders of magnitude differences, from the micro quantum level that some people say, to the cellular, to the synapse between neurons, to several neurons, to circuits of neurons, to whole brains, and some people go outside of the brain to say where memories are stored.
Right.
So I want to ask you, as an expert on Alzheimer's disease, which undermines memory, what can we learn about memory from when we see its destruction through Alzheimer's?
The question of where memory is stored in the brain, or even if it's stored within the brain, as opposed to, are we storing it on the cloud somewhere, as is a popular term now, I don't think we have the definitive answer yet. I think the answer may be partially true to both. I think we're storing some memories in the brain, some memories are in the cloud, and some memories are completely reconstructed by us. And let me give you some examples. First of all, we tend to think of memory as a thing, like a pen. It's not a thing. It's not something that a pen you put in a drawer and you pick it up. Memory is it's a constructive process in the brain. The brain constructs the memory fresh every time you recollect something.
That's a fascinating point.
There are 3 steps involved in memory. So the first step is the sensory perception. So if I want to remember something, I'm getting the information either from my touch, from my vision, from my hearing, and each of us hears, touches, feels things in a slightly different way. No two people's eyesight, hearing, etc. is the same. So that's one reason why 2 people may see the same thing, but their input is slightly different. So in that sense, it's a little bit like a computer. On the computer screen, you're typing some information, you're inputting some information. The first time the information enters the brain, it enters a part of your memory called working memory. So working memory is kind of like a temporary scratch pad, if you will. It's kind of like the computer screen. It's a temporary file. It hasn't been saved anywhere. The computer thinks this is not important stuff. If I crash, let it all go away. It's RAM memory, exactly. So your working memory, we don't know exactly where it is, but we think maybe the hippocampus and the frontal lobe is very important for working memory. And our working memory is very limited. It can only house a little bit of information. It's like, your temporary memory. Once we attach some importance to that memory, either emotional importance, safety importance, whatever, or if we practice it over and over again.
Focus on it.
Focus on it. Or we practice over and over again. We repeat the same thing. Then the brain says, this is important stuff, I got to keep it. And then what it does is the ultimate mystery. It then, so the current thinking is it then breaks that information down into thousands, maybe hundreds, maybe millions of bits. And then it distributes them throughout the brain. That's all we know. That's where our knowledge stops. Now, every time we try to recollect something, it then reconstructs that entire new memory, which is completely context dependent. We know that there are several regions critical for this reconstruction process. We know the hippocampus is very important, the entorhinal cortex is very important, because lesions in each of these areas have produced certain specific forms of memory loss, but that doesn't mean that that's where the memory is stored. It just means that the circuit has been interrupted there and the brain is not able to reconstruct the information fully. There are other times, as we get older, for example, we get a little slower in recalling something. That means something is going wrong with the reconstructing information process. There are yet other times where we have a false memory, which means as the brain is reconstructing information, it's pulling stuff out from some wrong basket.
What's incredible is that we have literally millions of memories in different forms. And if they're all stored globally in the brain and broken up into millions of pieces, the reconstruction process just seems astonishing.
Right. That algorithm must be mind-blowing. There's got to be some simpler ways of doing it because a lot of that is related to some basic elements. So if you take a rose, for example, we might break a rose down into its color. We might break it down into, I got pricked by its thorn, so that's got a fear element to it. I gave a rose to my fiancée before I got engaged, so it's got a love and emotion, and you see bouquets you give people for your secretary on her birthday. So the brain has to sort of take into account all of these past memories. And using your past memories, that's how it creates the present memory. So it's predictive because it says, what are all the ways when I want this picture of the rose to come in the future? What are all the pieces of information I'm going to need at hand to process it effectively? And that's how it stores it.
You made a comment that possibly some of this could be stored in the cloud.
Right.
I let that pass because I'm fascinated about all of this, but I'm not going to let it pass forever because that is it sounds to me, it sounded very normal when you said it, but it's a very controversial kind of comment.
Extremely controversial. Is there a collective consciousness? Is there a collective memory? Do we use, and at its simplistic level, we might simply rely on environmental triggers. So instead of storing everything inside, we might just take what's outside and then use that information on the context. So that's a simplistic way of thinking about the cloud.
Yeah,
but
and some philosophers now say that human consciousness must involve some externalities in a strong sense, not just in the obvious sense.
And I'll tell you a fascinating experimental paradigm that people are just now starting to take very seriously. It's a process called hibernation. And there is a little animal, it's called the Arctic squirrel, that's been studied now for a couple of decades. When it hibernates in the winter, its body temperature drops by about 30 degrees. Its brain activity slows down. There is massive neuronal destruction in the brain. But yet, when it wakes up, all of its neurons are reformed. So one of the interesting experiments someone wanted to do was, if I bury a nut that this particular Arctic squirrel loves, and I show the Arctic squirrel where I'm burying the nut just before it goes into hibernation, if the memory was truly stored in the brain and all these synapses were destroyed, when it came out of hibernation, it wouldn't be able to find it. But on the other hand, if it's not stored in the brain physically, it's stored in some cloud. When it came out of hibernation, it would be able to find it. And these squirrels are able to find the nut.
Yeah, I'm not sure the conclusion is entirely justified from the data, unless I have a lot of other experiments.
I agree.
But
it's using other cues as well. You know, it's probably using its sense of smell. It's maybe finding it freshly. You know, this experiment is not definite.
Or maybe every synapse is not being destroyed.
I completely understand. The brain might have multiple backup systems and multiple alternate pathways. And even in a hibernating animal, there are basic brain systems that are still going to keep the animal alive. So you're absolutely right.
Yeah, but I admire the guts to try to study something that other people would say you shouldn't even touch.
It's very hard to study, you know, because you could take brain dead people perhaps and do some experiments, you know, people who have had serious brain injuries and the memory systems have been destroyed.
You can never isolate it.
It's very difficult to isolate.
And the problem is that if the claim is you're storing a memory in some non-physical way, it's almost impossible to fully prove that in a physical manner. It's almost a contradiction in terms.
Right, and Alzheimer's disease is an example that neuroscientists would use to say, look, if the Alzheimer's patients were storing their memory in a cloud somewhere, then why are they having such severe disability and memory loss? Why are they forgetting how to drive a car? Why are they forgetting the face of their spouse that they've known for 60 years?
Right, and the argument of those folks who I talked to too, is that, well, they still have the memory, but they've just lost the ability to recall it. I think that's a cop-out.
Could be a cop-out. But they said the same thing for Parkinson's patients until they came up with a drug that woke them up from their, Parkinson-induced stupor, and all of a sudden all their memories were there. They're comatose patients whose brain activity is so badly damaged, and they come out of coma. There had been one patient who came out of coma 20 years later. And even though she didn't have a memory for the period where she was in coma, she still was able to recollect past information fairly accurately. So there's evidence that goes both ways, and it's like I said, we don't know that much about where the memory is stored in the brain.
But what is critical is that this concept of how memories are stored, where they are, is really enormously probative of what we understand human mind consciousness to be about.
Sure.
And it's still the case that very smart people vary it, not where in the brain, but enormous orders of magnitude.
Yes.
So
there's a saying about the brain which I love and which neuroscientists hate, even though I'm a neuroscientist. It goes something like this: if the brain were so simple that we could understand it, then we would be so simple that we could not understand it.
This is actually Sussex campus, where I work. And what we've done here is we've taken a kind of panoramic video of campus, and we've used the machine learning algorithm, which is very good at detecting or classifying objects in scenes. It's one of these so-called deep convolutional neural networks. It's very good. And what we do is we run it backwards. So we tell the network there are dogs, and the network then updates the images. And so it's not like just photoshopping dogs on. I mean, dogs are coming out of everywhere. The whole thing is suffused by dogs. So it's not actually like there's dogs in the sky. There's a few too many dogs around there. And I'm not saying this is equivalent to a psychedelic trip, but there are, some people say there are certain similarities. And the reason for doing this is, A, it's a lot of fun, but we can use it for open days and things like this. Come to Sussex, you'll have fun. But it gives us a way of getting, again, more detailed. So what might be going on within the brain that specifically leads to the sorts of phenomenology? And if, to the extent that that is similar to a psychedelic experience,
there was a renovation happening in the apartment across the way from ours, and I was invited in my dream world. There was a real renovation happening, and they took me around, and it was crazy in there. There were stages and performers and circus, all this crazy stuff. But what really caught my attention was the height of the ceiling, because I knew that the ceiling couldn't be that high. So I said to the contractor, "How'd you get the ceiling so high?" He said, "Well, the outside of the building has a different shape in this part of the building." And in the dream, I said to myself, "That's not true. I know what this building looks like. This must be a dream." And I said to myself in the dream, I'm going to wake myself up and prove that this is a dream. And I shook myself in the dream, and I shook myself in real life, and I woke up. And so I'd never had that experience before. It was kind of a wild moment for me. But I gather that this is something now which science really can confirm, that there is this thing called lucid dreaming, where you can be in a dream and know that you're in the dream.